Welcome to The Explainer. Today we're doing something a little different. I'm going to put you in the hot seat for a top-tier technical interview all about machine learning optimization. We'll go through the key questions, and you can see how you'd stack up. Ready?
All right, let's do this. You're in the hot seat. The topic is optimization. No warm-up, we're diving right in.
Okay, let's start at the beginning. Any good interview on optimization has to start with the fundamentals. I mean, before you can figure out how to navigate a landscape, you got to be able to describe the terrain, right? So let's talk about the calculus that lets us map this whole thing out. So, let's talk about this loss landscape. Picture it in your head, this vast, complex, hilly terrain, and our job is to find the absolute lowest point. To do that, we need to know two critical things at any given spot. Which way is downhill, and how steep is it? In other words, how do we measure the slope and the curvature of our loss function?
Exactly. And these are our two essential tools for the job. You've got the gradients, which is basically a vector that points straight uphill, the direction of the steepest climb. So, naturally, to go down, we just walk in the opposite direction. Simple enough. But then you have the Hessian. That's a matrix, and it tells us about the shape of the ground right under our feet. Is it a bowl? Is it a ridge? Or is it something tricky, like a saddle point? When that gradient is 0, and the Hessian tells us we're in a nice, bowl-shaped area, boom! We know we found a local minimum.
Okay, now things get really interesting when we zoom in from that single final loss value and start looking at what's happening between the layers of a neural network. That's where the Jacobian matrix enters the picture. Think of it as a generalization of the gradient. It's for functions that don't just spit out one number, but take in a vector and output a whole new vector. It tells us how every single output element wiggles when we nudge each input element.
And this right here, this is the kind of insight that separates a good candidate from a great one. Look, anyone can say backpropagation uses the chain rule, but a top-tier answer is explaining it as a series of Jacobian vector products. Why? Because it shows you get what's really happening. Each layer is just a function, and backprop is just chaining their derivatives, their Jacobians, all the way back to the start. It's the engine that makes deep learning work, and understanding it at this level is non-negotiable.
Excellent. You've nailed the calculus fundamentals. Now let's move from theory to practice. Let's talk about the absolute workhorse algorithm of machine learning, gradient descent.
So we know we need the gradient to tell us which way to step. But to calculate that gradient, we need data. And here's the practical question. How much data do we use for each step? Do we look at the entire data set to get a perfect but really slow reading of the landscape? Do we just grab one random data point for a super fast but noisy update? Or is the answer somewhere in between?
And this is the classic trade-off, right? On one end, you have batch gradient descent. It's stable, it's smooth, but man, is it slow and memory hungry. On the complete opposite end, you've got stochastic gradient descent, or SGD. It's lightning fast, uses almost no memory, and that noisy gradient can actually be a good thing. It helps you jump out of shallow local minima. But the real winner, the one we all use, is mini-batch SGD. It really is the best of both worlds. It's efficient, it's pretty stable, and it still has enough noise to give us good generalization.
Yeah, this is exactly why mini-batch SGD is the default choice for pretty much everything now. It perfectly balances that computational efficiency with the regularizing effect of the noisy gradients. But there's another huge reason: hardware. GPUs are literally built for this stuff. They are designed to do the exact same math on a small batch of data all at once. That's called vectorization. And that makes mini-batch training unbelievably faster than trying to process things one by one.
Okay, very good. You've got a solid grasp of the core algorithm. But in a real interview, they're going to push you on the modern toolkit. So let's talk about how we can optimize smarter, not just harder. This gets us into the world of adaptive methods and learning rate schedules.
Let's think about this for a second. Vanilla SGD. It uses the exact same learning rate, the same step size, for every single parameter in a network that might have millions or even billions of them. Some of those parameters might be for recognizing tiny little details and need small tweaks. Others might be for broad strokes and need huge updates. A one-size-fits-all approach feels kind of primitive, doesn't it? Can we do better? You bet we can. And what's so cool is you can see this beautiful evolution of ideas. First, you had AdaGrad, which was a great idea: give every parameter its own learning rate. But the problem was, the learning rates just kept getting smaller and smaller until they basically stalled out. So then comes RMSprop, which fixed that by using a moving average so it didn't get bogged down by the distant past. And finally, Adam comes along and basically takes the cake. It combines that adaptive learning rate from RMSprop with this idea of momentum,
a moving average of the gradient itself, which helps it blast through flat spots. It's just an incredibly effective all-in-one optimizer.
But even with a powerhouse optimizer like Atom, you still have this global learning rate you need to manage. And that's where a learning rate schedule comes in. It's really just a plan, a recipe, for how you're going to decrease that learning rate as training goes on. You might cut it in half every few epochs, that's step decay, or you might use something smoother, like a cosine annealing schedule.
So why is this so important? Well, think of it like this. At the beginning of training, you're lost. You're miles away from the solution. You want to take big, confident steps to cover a lot of ground quickly. So you start with a high learning rate. But as you get closer to that minimum, you need to be more careful. You need to take smaller, more precise steps to really zero in on the bottom. That's when you decay the rate. If you don't, you'll just overshoot the target and bounce around it forever. Getting this right is often the key to squeezing out that last bit of performance from your model. Okay, theory is great, but the rubber really meets the road when things go wrong. And trust me, they will go wrong. So for this final and maybe most important part of the interview, let's talk about debugging.
All right, here's the scenario. You've been training a big model for hours, maybe even days. You come in, check the training logs, and the loss has completely flatlined. It's just a flat line, it's not improving at all. This is a classic problem. So walk me through your diagnostic process, step by step. What is the very first thing you check?
A top-tier answer here isn't just a list of ideas, it's a systematic process. And here it is. Number 1, you always check the learning rate. Always. Is it way too high, causing your loss to explode or oscillate wildly? Or is it so low that you're just not making any progress? Number 2, look at the gradients themselves. Are they vanishing to zero or exploding into huge numbers? That points to a problem with your architecture or initialization. Next, check for overfitting. Is your training loss actually great, but your validation loss is stuck or getting worse? Then optimization isn't your problem, generalization is. And maybe the most important rule of all ML debugging, when in doubt, blame your data pipeline. You would not believe how often a silent bug in the data loading is the real culprit.
All right, pencils down. The interview is over. You've navigated everything from the Hessian matrix to debugging a flatlined model. That's some serious technical depth. But before we wrap up, let's debrief. Let's talk about the bigger picture.
So here's the thing. We've just spent all this time talking about our incredible toolkit for finding a minimum on that loss landscape. We know how to find the bottom. But here's the million-dollar question. How do we know the minimum we found is a good one? A minimum that will actually perform well on data it's never seen before? And that leaves us with the real challenge in deep learning today. Is the hardest part the optimization, just the mechanics of finding the bottom? Or is it generalization, the art and science of finding the right bottom?